Okay, so this is my talk for the German Probability and Statistics Days hosted in Mannheim. The title of my talk, as you can see, is a Cadillac Rough Path Foundation for Robust Finance. And so this is a joint work with Chong Liu and David Krummel. Okay, so as motivation for the talk, I'd first like to recall the notion of Fulmer integration. So let's suppose that we have some path S, and suppose that it has quadratic variation in the sense of Fulmer. So this means that we take, essentially means we take a sequence of partitions, I'll call Pn, with vanishing mesh size. And then, so we suppose that if I look at the squared increments of the path, and we sum up over all of the intervals in the partition Pn, then this sum converges as n goes to infinity to a function which we call the quadratic variation in the sense of Fulmer, which in particular is defined along this sequence of partitions. Okay, and then so Fulmer then showed that under this assumption, if I take a suitably nice function f, and so I denote here df to be the gradient of f, then I get the existence of this integral, which, as you can see, is given as a limit of left point Riemann sums. So again, it's a limit of Riemann sums along the specific sequence of partitions that I chose at the beginning. And then this integral comes, and in fact is defined via a pathwise Ito formula that looks like this. Okay, so the reason I bring this up is because, so there are advantages of the Fulmer integral, includes the fact that it is defined, as I say, as a limit of left point Riemann sums, which in particular means that this integral has a natural and robust financial interpretation. So you can really think of these Riemann sums as on each time interval. Okay, this is my investment, and then I observe the change in the stock price, say. So the fact that it's a limit of left point Riemann sums is really vital for the financial interpretation of the integral. As we've seen, it also comes with an Ito formula, which is very helpful in applications. On the other hand, the Fulmer integral, it's only defined for integrands of gradient type, not for general functions, which is a bit restrictive. And moreover, the integration map is not a continuous one. So the point of this talk is essentially to say, well, we want to be greedy, and I want a notion of pathwise integral such that all of these properties hold. So that is, I'd like to have a notion of pathwise integration, which has a natural financial interpretation, has an Ito formula, is defined for general, i.e. non-gradient type integrands, and is such that the integration map is continuous. So the way that we're going to do this is we're going to enhance the Fulmer integral using Cadillac rough path theory. So just to introduce this very briefly, so for this notion of integration, the integrators are going to be Cadillac rough paths. So that is pairs. So X we think of as the path, along with some enhancement or lift. There seem to be Cadillac and satisfying the usual conditions. If you're not familiar with rough paths, then you can just think of X along with this enhancement, where the enhancement can be thought of as encoding the information corresponding to the iterated integral of X against itself. Okay, and then the notion we use for the integrands so it's the notion of controlled paths from Gubinelli. So these are pairs, Y and Y prime, and the idea being that the increments of Y are essentially some linear transformation applied to the increments of X plus some higher order terms. Okay, so given an integrator and an integrand, i.e. a rough path and a control path, we then get the existence of the rough integral, which is defined as follows. So notice that here we have the usual left point Riemann sum, but then we also add this compensator term. And then this limit then exists along every sequence of partitions with vanishing mesh size. And then the rough integral that we get has then lots of nice properties. It also comes with a pathwise Ito formula. And moreover, the integration map, the map that takes integrands and integrators to the integral itself, is a continuous mapping with respect to the suitable rough path topology. Okay, so this integral has lots of nice properties. But as I say, we're missing the natural financial interpretation of the definition of the integral. So the way we're going to get around this is we're going to combine the notions of Fulmer and rough integration. And to do this, we introduce what's known as property Re from Riemann sums. So I'm going to show you what the property is, but maybe just to first point out that what the property actually is not the important thing. The important thing is firstly what you can do with it, and secondly, the fact that it is actually satisfied in situations that you care about in practice. So the reason I emphasize this is because the property itself, it's going to look at first glance like a bit of technical nonsense. But don't worry, you don't have to, as I say, it doesn't really matter. What matters is what comes after, is what you can do with it. But just so it doesn't seem so mysterious, I will just show you. So we take a sequence of partitions, Pn, nested and with vanishing mesh size. And then for a path S, so a CAD-like path S, let's write Sn for the piecewise constant approximation of S defined along the sequence, along the partition Pn. And then we assume that these approximations Sn converge uniformly to S. We also assume that the Riemann sums obtained by integrating Sn against S also converge uniformly. And we assume this inequality. It's quite technical, but essentially this term means that we get some p-variation regularity on the path S. And then this term means that we also get some regularity on these Riemann sums along the particular sequence of partitions that we're considering. But anyway, as I say, this slide, you can just ignore it. Don't worry if it doesn't make any sense. Pay more attention to this slide. Okay, so what matters is what you can then do once you assume property Re. So if S does satisfy this property with respect to some sequence of partition, then one can show that S admits a canonical rough path lift. So it is a rough path. And then moreover, we get this main theorem. So this is the main technical achievement, which says that if S satisfies this property, if we take an integrand, i.e. a controlled path with respect to S, and we assume that its jumps all lie in the union of these partitions, of course, this is a dense set, so this is not a restrictive assumption, then the rough integral of y against S can be written in this form. That is, it is a limit of left point Riemann sums along this particular sequence of partitions. So this is exactly in the same spirit as the Fulmer integral, except that it is also equal to a rough integral. So the integral, as I say, is given by a limit of left point Riemann sums depending only on S and Y and on the sequence of partitions that we've chosen. So we recover the natural financial interpretation of the integral. And moreover, we still maintain all of the useful properties of the rough integral. So it's still defined for non-gradient type strategies, it still has an Ito formula, and it's still a continuous map. Okay, so I mean, this is all well and good, except it's only really helpful if we know that we actually have integrands and integrators in situations that we care about, such that we are actually in this framework. So just to give some examples, for example, you can take if you consider a functionally generated strategy, so just some integrator phi, which is given as some nice C2 function of the underlying price path. Then one can define the corresponding capital process just in the natural way. So you think of the ith component of F as your investment into the ith stock, say. You then observe the change in the stock price. You sum over all of the stocks, you add up over all the time intervals and take a limit. And then the proposition says that any such functionally generated strategy is a controlled path, i.e. it is an admissible integrand in this framework, so that the corresponding capital process is well defined as a locally uniform limit. And moreover, and then that the power of rough path really comes in and says that I get nice strong continuity results. So in particular, the mapping that takes generating functions to the corresponding capital process is itself a locally Lipschitz continuous map. So we really get nice continuity of our strategy. Okay, and then another quick example. So we can consider Cover's universal portfolio. So this is defined as a mixture portfolio. So take here, say, functionally generated strategies just as before, but then integrate over some family of generating functions. Then given suitable integrability, then the universal portfolio is itself another controlled path and hence an admissible strategy in our framework. Okay, and then finally, So we have integrands that we, in our framework that you might care about in practice, but of course, none of this is meaningful unless this property re that we introduce is actually satisfied in situations you care about. So just to point out that, for instance, a general semi-martingale, any Cadillac semi-martingale will satisfy property re, almost surely. Moreover, a slight generalization of the notion of semi-martingale is the notion of a Young semi-martingale. For time, I won't go into any detail, but just to point out, Young semi-martingales also satisfy property re, almost surely. And moreover, typical price paths in the sense of BOVC also satisfy property re. So there are various situations which you might actually care about in practice where this property is indeed satisfied. And so you can actually make use of this framework. So in summary, the rough integral exists, as we've seen, as a limit of left point Riemann sums under property re. So we maintain the financial interpretation of the integral and have all the nice properties of rough integration. Many common examples of trading strategies are admissible in this framework, and this mysterious property re is actually satisfied in various situations that you might care about. So what we've provided here is more of a framework, but just as an example of an application that we've already found is to model-free stochastic portfolio theory, which is a joint project with Krista Kuchiro, Chong Liu, and David Prummel. Okay, if you made it this far, then thank you very much for watching, and I'll leave it there. So see you at the conference.